Hello again. In this video, I'm going to introduce the laboratory determination methods of fluid saturations. You're already familiar with the concept of fluid saturation, and in this video, I'm going to talk about how experimentally we can measure those from the core samples. So, alright, so there are two main methods. One is called basically retort distillation. Another method is called solvent extraction or thin Stark extraction. Okay, so we'll talk about each of them separately. So I'm going to talk first about retort distillation. What is the advantage? What are the advantages? What are the disadvantages? And we will solve a problem on that too. Okay, so retort distillation, the idea is based on vaporizing the fluids inside the core sample. So what happens is that you can see the apparatus in this slide. What happens is you have a piece of core sample, right? And you put it into this apparatus. Let's assume that here is your core sample, and there is a heater here. So these are the heaters, right? Heating elements. These are the temperature that it's going to work on, and it applies the heat to the core sample. So what happens? The temperature starts from room temperature, right? So T is equal to, I don't know, room temperature 70 degree Fahrenheit, that's T1, right? And the temperature starts to increase, right? Until it reaches to 212 degree Fahrenheit, okay? Once we reach that temperature, that's the boiling temperature of water. So what happens? The first thing that vaporizes from the core sample is water, okay? So the water starts to vaporize, and what happens to that vapor? That vapor, there is no way to go out from the top. The vapor basically go down then, okay? So the vapor go down until it reaches to this point, right? What is here? Here is a cooling water which is coming in and makes this system cool, right? And this is where it lives. Okay, so once the vapor reaches this area, it condenses back to liquid. Okay, makes sense so far? So once it condenses back, what happens? You will have it basically dropped into graduated cylinder, and then you have a volume of water which you can measure, right? How can you use that volume to calculate the saturation? Pretty simple. Volume of water divided the pore volume, right? You need to have the pore volume, so that should be a known value. You get the volume of water from graduated cylinder, and you calculate the water saturation. Now, how about oil? Oil boiling temperature is usually much higher than water, okay? So you have to go all the way to 1000 to 1100 degree Fahrenheit until the oil starts to vaporize. Okay, so once you reach that temperature, then the oil starts to vaporize. Exactly the same process, goes down, cools down, and finally you have your oil droplets basically condenses into liquid into the graduated cylinder. So you can calculate the volume of oil too, right? How can you use that to calculate the oil saturation? It's simply volume of oil divided by pore volume. Okay, makes sense? Alright, I can't ask if you guys have any questions, but please shoot me an email or just use my office hours in the Zoom so we can discuss it further. Alright, anyway, so that's basically this, right? How can you calculate the gas saturation? Remember that relationship, gas saturation is 1 minus SO minus SW, right? So you have your gas saturation just by simply using this equation. Okay, all right, awesome. So let's move on. Let's talk about the disadvantages and advantages of this method. It's a rapid basically method. It's a direct measurement, so it means that you directly measure the volume of water which is inside your core sample. You also directly measure the volume of oil in the core sample, right? And it has some accuracy, but it's not as accurate. So one of the disadvantage of this method is basically you have to use very high temperatures, 1000 to 1100 degree Fahrenheit. What happens to your core sample? Yes, it will destroy, right? It will destroy your core sample, and that's one of the main disadvantages of retort distillation method. Okay. Another issues that we have with this method is related to uh, accuracy of those measurements. How accurate are really those measurements? So regarding the water volume, there is one issue which is basically the main issue with this method, and it's basically we will have more water than what is actually uh, inside the core sample. With the core sample, I don't mean the whole core sample. I mean basically the pores that are really accessible by liquid. Okay, so what do we have inside the core sample? We might have different types of rocks, right? One of these basically main minerals that we have inside our rock is clay, right? Clay is one of the most important ones. Clay is a type of mineral that is basically the structure is such that there are multiple layers of silica on top of each other. So one layer, then we have another layer, then we have another layer, as you can see in the picture too. So multiple basically layers of silica and aluminum atoms and magnesium and oxygen and also hydroxyl group, right? So these are what clay is made of, right? So we have all these layers, and between these layers basically there is water. Okay, so water is in between these layers, and it's never accessible. I mean, these fluids, these waters that we have between the layers of clay cannot be produced. Okay, but once you increase the temperature very high, that heat will basically also transfer to these interlayers and vaporizes these water, and somehow these waters through small pores they will leave your core sample and they will be produced back into the graduated cylinder, right? So we have an extra volume of water which we really do not consider it as water saturation, right? So this extra volume results in inaccuracy of our measurements. Okay, so what this is one of basically the main issues. And if you look at this curve, this is determining water of crystallization. Look at this plot. So in the x-axis you can see there is a time, right? In the y-axis we have water recovered, right? So look at how water is changing with time. Can you guess what is this time that there is no water produced? Think about it. Well, uh, this period of time that we don't have any water produced is the time that requires the temperature from 7 it reaches to 210 degree Fahrenheit, which is the boiling temperature of water. So there will be no water produced, right? And then the vapor produced condenses, and the volume of the water starts to increase in the graduated cylinder, and then kind of reaches a plateau for some time, right? And temperature is keep increasing, right? So once the temperature passes 210 and reaches maybe 1000 degree Fahrenheit, maybe the temperature here is still 210 degree Fahrenheit. The temperature then starts to increase, and here the temperature might be 1100 degree Fahrenheit, and that's these basically volume is the volume of basically water recovered recovered from, sorry for my handwriting, inter layers. Okay, so this volume, which in this case is around maybe 4 milliliter, 4 cc or less, a little bit, right, is the water of crystallization. So you should not account for this volume when you calculate your saturation. The only volume that you should use is basically this volume, which is around 6 point something. So if you calculate your water saturation, then your water saturation should be 6 divided by your pore volume, whatever that is. Make sense? Alright, so that's basically the water of crystallization, and that's how you fix it and how do you calibrate basically your system, right? Another problem is basically called basically coking and cracking. So cracking is basically if you have a long chain hydrocarbon, let's say this is your oil made of basically hydrogens. These are all hydrogens. I'm not putting all the names there. You might have seen this in chemistry, right? If you have a long chain alkane and then you increase the temperature of that alkane, what happens is some of these bonds may break, right? If you break these bonds, what happens? You will produce some lighter components, right? And those lighter components you may not be able to condense it back with basically the temperature of your condenser, because their condensing temperature is very low. It's minus, I don't know, 30°F. You need that low temperature in order to be able to condense back these cracked organic materials, right? So you may not be able to condense back into the graduated cylinder, right? So so that's called cracking, right? So cracking is an issue, right? You may not recover back all the oils. You will underestimate eventually whatever oil you recover, right? Another problem is coking. So if you increase the temperature and you have basically a solid, right, and you may burn some of these oils, and what happens if you burn? You probably have seen some black layer on the surface of some solid or anywhere that is burned, right? That black layer is called coke, right? Coking is basically once you burn some of these organic materials, a layer of solid will be formed on the surface of that solid, right? This is called coke, and again will result in underestimation of whatever oil is inside your core sample. So that's another problem. Okay, all right, cool. So how do you fix it? There are many ways. This is one way, basically using some calibrated curves. You basically, for example, uh, you have basically 0.6 cc recovered, right? And actual amount was 0.8, right? So that's 0.8 that you have to use. Sorry about this. So 0.8 is basically divided by pore volume is your oil saturation. So that's one way, right? Another way is to use this curve that depending on oil gravity, whatever oil gravity you have, you go there, you get a factor, right? And then what happens, how do you use that factor? Whatever oil saturation you recovered, right? For example, I recovered 10 cc from the retort distillation method, right? My oil gravity, API gravity is equal to 40, and then I get this factor. This is a correction factor, okay? Let's call it F. F is around, I don't know, 1.15, right? So what you do is your actual volume of oil is that 10 cc multiplied by 1.15, right? And that gives you 11.5 cc, and that's what you use to calculate the oil saturation, whatever pore volume you have. Okay, I think we will use this curve and not the previous method, but we will use this curve to calculate basically the oil saturation. So here are all the formulas you need for retort distillation method. Of course, don't count the water of crystallization for oil. Make sure you use the correction factor multiplied by the measured volume, that's your volume of oil. Then this is the oil saturation, simple calculation for gas saturation. Alright, in next video we'll do an example which is basically this slide.